Last time we talked about controlled experiments. We take two units that are identical in every variable, except you treat one and you don't treat the other. Today we're going to talk about randomized experiments. This is where you take a lot of units and you randomly put some of them in a treatment group and some of them in a control group. And in the treatment group, you treat everybody, and in the control group, you don't treat everybody. So why would randomization help us learn about causality? Well, in a controlled experiment, you have your two units, they're identical in everything, except one is treated and the other is not. In a randomized experiment, think about the time right after you've randomized everybody, but before you treat people. Well, in that case, the two groups are identical, the control group and the treatment group. Okay, because by the definition of randomization, you've arbitrarily split everybody up into these two groups. So there's no difference between the two, except that you're going to treat one and you're not going to treat the others. Okay. Well, what do I mean by there being no difference between the groups? Well, suppose we pick one person from the treatment group and another person from the control group. It's very unlikely that these two people are going to be exactly identical in every single variable. But when we compare the average value of a variable in the treatment group with the average value of a variable in the control group, we're going to get the same number. And that's just because the distinction between these two groups is arbitrary. That's the definition of randomization. There's no systematic difference between the groups. Now, suppose that in practice we had our treatment group and our control group, and we looked and we saw there's a lot more women in the control group, for example. Well, what that would mean is that women were a lot more likely to be assigned to the control group than men. That's not possible with true random assignment. So a different way of saying this is that randomization produces balance in the variables across the two groups. Okay? Mathematically, you would say that the assignment to treatment is statistically independent of all the other variables, like gender. So gender and whether you're assigned to treatment or not is uncorrelated or independent. Now, it's helpful to remember that there are three kinds of variables we're looking at: our outcome variable, our treatment or policy variable, and our pre-treatment variables, which are all variables that happen before treatment. Okay? Randomization produces balance in the pre-treatment variables, like gender, but it doesn't produce balance in the treatment variable. That's the whole point. The treatment group gets treated, the control group doesn't. Okay, so now we can see what the main result of randomized experiments is. Because these two groups are identical in all of their pre-treatment variables, okay, the only thing that's different across the two groups is treatment, whether they're treated or not. Then any difference in the average outcomes between the two groups can be completely attributed to differences in the treatment status. Okay? So if we see the average outcomes in the treatment group are higher than average outcomes in the control group, we can say that's because treatment has a causal effect on outcomes. Now, this argument requires there to be a large number of people in each group. Think about controlled experiments once again. That required us to have just two people. We could get causality with just two observations. And that's because we had two observations which were identical in every way except for their treatment status. Well, now in the randomized case, suppose we looked at a really extreme case where we just had two people and we randomly assigned one to treatment and the other to control. Well, I randomly assigned them, so can't I just look at the difference and learn causality? Well, no, not really. And that's because if you take those two people, they're not going to be the same in all their variables. Okay, so you can't conclude that the only difference across the two groups is because of treatment. It's only once you start getting a very large number of people in each group that you can reasonably say that the groups are identical. Okay, and therefore the only difference between them is whether they're treated or not. This is one of the major differences between randomized experiments and controlled experiments. Now in practice, you're going to have to figure out, well, just how many people do we need? And there's a whole body of techniques for doing that. in statistics. We're not going to talk about that. You can go look it up. But basically, the causality idea says you need a lot of people. Okay, and statistical inference and other statistical techniques will quantify exactly how large you need. Now, in practice, there's a lot of benefits to doing randomization. One is that it makes data analysis very simple. Basically, when you have a randomized experiment, you're just going to have to compare the average outcome in the treatment group with the average outcome in the control group, and the difference is going to be an average treatment effect. So it's going to tell you something about causality. And we're going to go through a lot of examples of how to analyze randomized experiments in the next few modules.